So here's another example of something that can be modeled by a sinusoidal function. When the water comes in and out, the tides, it happens on a cycle. And it becomes important to predict those things because certain boats can get in and out of a harbor at a certain time depending on the tide. So you kind of want to know that information. Because you go to take your big boat out and it's at the wrong time of the day and you get stuck, or, you know, who knows? There's other reasons that you would want to know what the tide is doing at a certain time of the day. So here is an easy word problem because the equation is given to us. So on all ones that the equation is given to us, we don't have to figure anything out. It tends to be an easier type of problem. But as we look at this equation, we can see that the numbers aren't nice whole numbers because this is a real life example. We've got some decimals and we've got a really interesting and strange b value, 0.16 pi times t. So we're going to sketch this graph. And again, we're going to use the same techniques that we've done all the way along. We're going to use our DAB-C. We're going to look at our sinusoidal axes and graph everything before the horizontal, or before the translation. In this case, do you see that there's no c value? And so this one, we just have to dab. So it's going to be awesome. All right, here is all the information. I'm not going to get you to write this down, but there is a reflection over the x-axis. We know that our amplitude is 4.5. Our period, if we do 2 pi divided by the b value, and you type that into your calculator, we get a period of 12.5 hours. There's no shift, and our sinusoidal axis is at 13.7. So I'm going to just erase that so we have some room to make our graph. Again, when making our graph, notice that I put my x-axis kind of low because I already knew that my sinusoidal axis was at 13.7, which is quite high. And I know that my amplitude is at 4.5. So I'm going to choose 13.7 to be there. And then I can say, I know that that is my sinusoidal axis. And then based on that, for my a value is 4.5. Just looking at the distance that I chose for 13.7, can you see that about there for going down 4.5 seems reasonable? And then I would go about up the same amount for 4.5. So if I subtract 4.5 off of 13, I get 9.2. If I add 4.5, I get 18.2. So those will be my max and my minimum values. My period, when we did 2 pi divided by 0.16 pi, we got 12.5. So I'm going to mark 12.5 somewhere along my x-axis and then divide it into 4 equal sections. Wow, that's an ugly 2. 6.25, half of that will be 3.125, and then this will be 9.375. So we've got some bigger decimals that we're working with than we've had before, but the idea stays the same. I hope that we're starting to get a sense, because we've done a lot of these, that starting with our d value, then getting our maximum and our minimum from our amplitude, and then figuring out our period and dividing it into 4 equal sections, then what kind of graph do we have? We have a negative cos graph. Where does a negative cos graph start? It starts at a minimum, back to our center line, to the maximum, back to the center line, and then to the minimum. And now normally we would draw this with a dotted line because this would be our temporary graph before we do our shift. But in this case, we don't need to. In this case, we don't need to because there is no shift. Now, as we get used to working with graphs, we're going to be using our graphing calculator to figure out a number of questions. So the next question, I'm going to show you how to do that. Yes? So there's no shift because if we look at the equation inside here, you see that there's no c value. It's not 0.16 pi t. You could say plus 0 at the end because it's not inside the brackets. You're not adding or subtracting anything, which would make that horizontal shift. So the next thing that we're going to learn how to do, because in part B it says a bulk carrier needs at least 14.5 meters of water to dock safely. So if we look at our graph, what that's saying, 14.5 on our graph would be about here, right? And if we draw water, yes, get to use my artistic abilities. If we draw water, does it make sense that the boat is only going to be safe from here to here and in this section? Because in that section, the water is deeper than 14.5. Any other time, and it's going to run into some problems. In the IB course, there are a number of questions that, especially next year, there are a number of questions that can only be solved by knowing how to use your graphing calculator and knowing it well. In the grade 12 pre-calculus course, they tend not to put any of those questions on there, but we're doing this to help you get ready. Okay, I'm going to show you how you would solve part B using trigonometry and using our old techniques that we've already learned, because those will be expected of you in university. And I'm going to show you how you can use your graphing calculator to solve it, because solving it with your graphing calculator is really fast and easy. And one of the things that this course and next year's course want to teach you is sometimes we can solve complicated problems quickly if we know how to use technology to do that. Okay? Sometimes it's really simple, like the sunset problem that we did the other day. You said, well, I should just Google it and get the answer really quick from Google. But someone had to put it on Google to begin with, and they had to figure that out. So we have to also realize that sometimes there's beauty in being able to figure things out for ourselves. So the first thing we want to be able to do is we want to be able to put this graph exactly as you see it right here on your calculator. I want that curve to show up. A couple of things to notice about our equation. Since we're using our period as 2 pi over our b value, are we thinking in radians or are we thinking in degrees? We're thinking in radians. So when we turn on our calculator, we want to make sure that our calculator is in radians. So we can start by hitting our mode button and checking, and my calculator is already in radians, so that's good. The next thing we can do is we can go to y equals and we can type in this equation. So for our equation we had negative 4.5 cos 0.16 pi x bracket plus 13.7. Now, if you just push graph at this point, chances are you won't see anything, or if you do see something, you don't see very much of it. Okay? Because we want to have this. And this is the nice thing about being able to graph it on your own, because you need the skills to be able to graph it on your own, because we want to set our calculator window to look like that. That's what our screen window wants to look like. We don't want that window to be up over here or over there where we can't see any of the graph. So now if I put this box around here and I think about that, I'm going to go to my window right beside y equals and say, what should I be looking for? I want to see from 0 to 12.5 for sure. So I'm going to go into my negatives a little bit. Maybe I'll go to -5. That way for sure I can see my y-axis. Because if you don't have any negative values, your y-axis is not going to show up. And since I want to go up to 12.5, I'm going to go a little bit further. Maybe I'll go up to 15. So can you see that that would see about from -5 to 15? We'll see a nice amount. Notice how we mark things every 3.125. One of our ticky marks was 3.125. So you can even set your scale to be exactly that. I'm going to go 3.125 for X SCL. That stands for X scale. And that tells you where they're going to put those ticky marks along your x-axis. For my y-min, a -1 makes sense. What was our maximum? We went up to 18.2. So maybe I'll go up to 20. Your y scale, you can't make it perfectly so it hits 13.7. So maybe you just want to make your scale go up by 5. So you can easily sort of estimate where things are at. 5, 10, 15, 20. Now when we hit graph, we get a graph that is identical to the one that we graphed. And now in part B, we're wanting to find, if we go back to our graph, we're really interested in this point and this point. Because that's going to be the times where our water is 14.5 meters or deeper. So how do we do that on our graphing calculator? We go back to y equals, and if you want a horizontal line, how do you write an equation of a horizontal line? It's just like y equals whatever that number is. So into y2, I'm going to write 14.5. And when I look at that graph, that draws that horizontal line at 14.5. Your calculator, you've probably done this before already, but just a reminder, your calculator has things built in to find out where two graphs intersect. So that's under second trace, which above that says calculate. Number 5 is an intersection. And once you have that intersection on, you can push enter 3 times and it will always find the closest intersection to where your cursor is. So do you see my cursor is close to this one right here? So I can just push enter first curve, it jumps to the second curve, push enter second curve. It always asks you to guess. So if you like guessing things, you could guess the number and see how close you are. And then it calculates it at 3.48. So we know our first one here is at 3.48. If we want to calculate our second one, we go through those same steps. Second, calculate. Number 5, intersect. But I'm not going to push enter 3 times because now my cursor is on the one that I already found. So I got to use my arrow keys. Right? And this is time consuming, especially on this one. So I'm a little bit over the, now I'm closer than the other one. If you want to be for sure, you can keep getting your arrows until it's really close. But if you like to live on the edge, you can see how close, how far away you can get it and still get it. Push enter 3 times. And the other one's at 9.02. For how many hours per cycle can it dock safely? Well, that's from 3.48 to 9.02. If we subtract those, what do we get? 5.54. So So this is definitely a calculator question. Now, when you get to university, there may be some times that you have a question like this that you're required to solve, but not using the graphing calculator's graphing function. That makes it a lot longer and a little bit more tedious, and you have to be really good at solving sine and cos equations. I'm not going to get you to write this down, but I'm going to show it to you so you can see it, and if you want to watch it later on the video to see if you could understand it a little bit better, that'll be fine. So if we were going to solve this with our calculator but not using our graphing calculator's graphing functions, just solving it algebraically, you want to find out where those graphs intersect or where they hit at 14.5. So what you know is you know the depth, and you can plug that into the equation for your y value. And once you plug in 14.5 for your y value, then in your equation you only have one thing to solve for, and that's t. So you should be able to do that, because as soon as you get down to one variable, you just have to use your skills, algebra skills, to get that variable by itself. And that variable is inside a cos function, so you're also going to have to use your skills with solving trig equations, which we've done some already. First thing you would do is move your 13.7 over to the other side, divide by negative 4.5. That gets your cos all by itself. Now, these numbers that we have right now, they don't look nice. How are you used to solving cos equations? Your cos equations usually look like this, with somewhat nice numbers. Cos theta equals 1/3, or cos theta equals negative 1/3. And if you had those nice numbers, you would look and say, oh, it's not on my pi plate. I have to find my reference angle. Because cos is negative, it's in quadrants 2 and quadrants 3, and then solve from there. Well, in this case, we have that same idea, but instead of a nice theta, we have a 0.16 pi t. Not quite as nice a looking number. And instead of nice numbers like negative 1/3, we got some decimals, 0.8 and negative 4.5. I actually think that this side isn't as big of an issue, because those are still decimals in there. But what are we going to do with that 0.16 pi t? So a strategy that you can use is you can say, well, if this is nicer, why don't I just make it nicer temporarily? Why don't I just let theta equal that whole inside so that my equation looks more like I'm used to? Cos theta equals that. And now this question is fairly simple. We need to find our reference angle. How do we find our reference angle? We do cos inverse of the positive value and get a reference angle of 1.392. Then we have, it's going to be in quadrant 2 and quadrant 3 because it's negative. So we can do pi minus our reference angle in quadrant 2 and pi plus our reference angle in quadrant 3. And we get two answers for theta. So this is exactly like we've solved for theta in the past. Once you get your two answers for theta, well, now we have to work backwards and say, since my one answer for theta was 1.7495, that theta was actually equal to 0.16 pi times t. If I want to find out what t is, I'm going to need to divide by 0.16 pi. Now, the most common mistake that students make at this time, I'm just going to look at the numbers here, 1.7495. They go to their calculator. They go 1.7495 divided by 0.16 pi, and they get the wrong answer. But isn't that exactly what it said? Okay, what did I do wrong? I need brackets on the bottom, because technically what your calculator does here is it does 0.7495. It divides by 0.16. It gets an answer, and then it multiplies by pi when you really want to divide by that pi as well. So you either need brackets on there, or if you start getting used to using the fraction button, Whoops. What did I type in wrong? Oh, I put an H instead of a pi. There we go. That is our better answer. Now, did I type in anything wrong when I typed it in? Why did we get 1.7495. I forgot the 1. So let's actually just make sure that this is. If you forget a number, do you know how to use the insert button above the delete button so you don't, because otherwise when you type things it just types over top. So that insert button also can be handy. So if you had 1.7495, then sure enough, it does work out to exactly the same answer that we got with our graphing calculator. So now you have to decide what was faster. If you get good at your graphing calculator and plugging in an equation and finding intersection, it can be much quicker to solve that way than solving algebraically. Similarly, you could find out the other angle in quadrant 3, work the same way, and you get your 9.02. So all of those things together help us solve that it's 5.54 hours. So that's how we could do that with our calculator, but without the graphing function, using what you know about your cast rule, reference angles, and what was new about this equation was that technique that I showed you where you temporarily substituted theta for the 0.16 pi to make the question look like something you were used to, and then switching it back. And that's a good math strategy that is used often. When something gets too complicated, make some substitutions to make it temporarily more simple so you can work with it, and then you bring back the complication later. All right, here's our second example. It's a Ferris wheel 1. It's much faster than the last Ferris wheel, and it's got a 15-meter radius, so that's pretty big, I think. So again, we want to graph this. This is harder to graph than the first one. The first one, we had an equation. And in this second one, we just have some information. So whenever we have information, first of all, you can draw a picture. So fun times, draw your Ferris wheel. Put some chairs on there. You know, you can even put some people on there, daredevils with no hands, hands up in the air, because the Ferris wheel is the most scary amusement ride you can think of. 20 seconds, we should really make it rotate in 2 seconds and change the radius to 15 kilometers. I think that if it was 2 seconds and 15 kilometers, you could actually calculate how fast you'd be traveling around that Ferris wheel. I think at those measurements, you'd probably die. But fun times. Anyway, we should have some, here, got to get some spokes. Otherwise, it's not probably very safe. Okay, so there we have our daredevil person right at the top, hands up in the air, and we're going to graph this function. Drawing the picture off to the side can really help me because I'm going to set my axes, ground levels here, so you can really see how the graph and the function go together. You're getting on 1 meter above the ground, so that means this part here is 1 meter. Ferris wheels that don't go up 1 meter or go into the negatives are dangerous. So we want to make sure that the bottom is a little bit above ground. 1 meter above the ground. It has a radius of 15 meters. So does that help us? What's our center line going to be at? Our center line is going to be at 16, and our maximum is going to be up here at 31. Well, I think just so that matches up with my graph a little bit better, Looks like my center of my is right here, so I'm going to put that there. My maximum's right there. It looks a little bit more realistic based on my picture. And it rotates every 20 seconds. So that means that our period is 20 seconds, and we can mark 20 seconds somewhere along here and split it up into 4 equal sections. 5, 10, 15, and 20. Where do you get on? You get on here at the bottom, and you know 20 seconds later you'll be back to the bottom. Where will you be at 10 seconds? At the top. And at 5 and 15, you'll be in the middle. And here we have our graph. And as far as labeling our graph, this time not only do we need to put our numbers on our graph, but here we have time. So we can write down here that this is time, and it's time in seconds, so we can write the units that go with this. And along our y-axis, we can label this as our height, and our height unit is in meters. So we're also going to be really careful about labeling things. So if we have information, we can label its time along the bottom, height along the side. Looking at the graph, it says estimate. When is it going to be at 22 seconds? Oh, we haven't found the equation. We're not done A. Whew. Sorry, I got a little ahead of myself there. We have to find an equation for this. Okay, off to the side, what's the amplitude? What's the center line? What's the B value going to be? 16 is our center line. Amplitude, 15. B value is 2 pi over the period. And this time I'm not going to simplify it, because I like the formula. When you have things written as 2 pi over 20, you can see right there that 20 is your period. If you simplify it to pi over 10, or even the last question, which was 0.16 pi, it's not easy to see what the period is. And so what you'll see often when people are working with these equations, like in the last one, they would have left it as 2 pi divided by 12.5. So you can see right in your equation what the period is without having to do any kind of thought. So I'm going to leave it as 2 pi over 20. Let's find an equation with sine and cos. Again, I can write everything out. A is 15 for both of them. You do one in sine, one in cosine. My B value is 2 pi over 20. I can write that in for both of them. Leave space. And then my D value is plus 16. So the dab part is going to be the same for sine or cos. Where does sine start? Middle going up. That's that point right there. So we would have a shift of 5 to the right. Do you want to do a cos graph or a negative cos graph? Negative cos graph. So let's put a negative in front, because then we don't have any shift. You could write plus 0 in there if you wanted, but you could just write x, because you'd have no shift. And so the second graph is probably our nicest graph, because it's the shortest, and it starts right at the place where we start on the Ferris wheel. And now we can look at part B. But I want you to practice using your graphing calculator. So right now, I want you to get this picture on your graphing calculator. If you can get the Ferris wheel on your graphing calculator, then that'll be really impressive. So if we're going to our calculator, go to y equals, clear out previous stuff. I'm going to type in the negative 15 cos bracket. I'm going to use my fraction button here. 2 pi divided by 20 x plus 16. So I've got my equation in there. I'm going to go to my window. I want my x to go from negative 5 up to 25. My x scale's going up by 5s this time. Y min from negative 1 all the way up to maybe 40. And there I have the graph just like we've drawn it. Yes? So sometimes you do what appears to be everything right, and then you get a problem, like it says invalid dimension. So I want to show everybody what is the most typical problem with that. If you go to your y equals, at the very top of your y equals it says plot 1, plot 2, plot 3. Now sometimes you're going to be doing statistics in other courses like chemistry. Sometimes you're going to do statistics stuff in math. And when you graph that statistics stuff, you end up turning one of your statistical plots on. And so if one of them are on, it's going to show up like this when you get to your y equals. One of them is going to be blacked on. And if you change your window so that the points in your statistics no longer show up, your calculator is going to tell you there's a problem with your window because it thinks you want those points to show up. Now, all you have to do is go up to that plot, push enter on it to turn it off. It doesn't delete your data. So if you still need that data later for chemistry or for sports, exercise, and health, then it's there. But now it'll let you graph things. So that's one problem-solving thing that comes up often, especially as you start using your graphing calculator more and more for statistical things. So I wanted to point that out. Now in part B, it says estimate the height after 22 seconds. The word is estimate. That means you can just look at your graph. Guess where 22 seconds would be? Well, don't guess. You should be able to figure out that it's right there. Okay? But then, what do you think that height would be? 4 meters? Okay. So, if we're estimating 4 meters, that's just an estimate. The reason I got you to put things into your graphing calculator is, in real life, you would want to know exactly. Okay, so how do we use our graph that's right here to get that value exactly? So I'm going to let it graph. It's graphing so fast, so exciting. Wonder what's going to happen next. It went up. Okay, we can go second and calculate. And under calculate, there's a bunch of different things. When you want to calculate a value, it's just the first one, value, and you can just type in 22. Now, it's only going to work if your window includes 22. So if your window only went up to 20, it's not going to work. I made my window go up to 25. So now it comes out at 3.86, and you feel like I didn't need, my estimate is so good at 4 that I'm amazing. But 3.86 is the actual answer. So when you're estimating a value, you can just put in the number. And if you want to find multiple values after your first one, once you're on this, you can just keep typing in different numbers. Like, what is it at 17? Boom, it tells me. What is it at 16? And you can just keep typing in numbers, and it will keep telling you those answers. You don't have to go second calculate value over and over and over again. For part C, estimate what time you'll be 20 meters above the ground. So now we're asking this question. 20 would be here. Well, there'd be one time there and one time there. Somewhere just after 5 and somewhere just before 15. So what are your estimates going to be? 6. And if it's 6, which is 1 away from 5, Our other estimate should be 14, because that's 1 away from 15, because our sine graph is symmetrical. Now, how do we solve that one with our graphing calculator? Well, now we would have to go to y equals. We would have to type in 20 into y2, look at that graph to draw that line, and then find out where they intersect. So second, calculate. Number 5, the intersection. Enter, enter, enter. It'll find the closest one. 5.8. We said, we are amazing. We said 6. And if you want to find the other one, second, calculate, intersect. Now you're going to have to move your cursor so fast. I have to do mine extra slow because if I hit the buttons too quickly, the whole calculator on the computer crashes. That looks like enough. Yes. And we said 14, and it's 14.1. We're so amazing. All right.